No, not 6.6. 6.67 is the G. Big G.
Oh.
6.67 times 10 raised to negative 11. That's the Newton constant. I think Newton is not happy in the graph yet.
Wait, is it
Newton's not just not happy. He's rolling like a wheel in there.
There's the mass of the earth.
Oh, Jesus. Okay, wait.
I'm gonna cry.
I got it.
How
Next
can it
he-
be mass of the
Next,
earth?
he's gonna write 9.81.
Oh, he's cheating. He's cheating. He's cheating. Okay, no,
Wait.
that's not allowed. Okay.
No, you can't just
Okay.
do that.
Okay, write it down.
No.
1.25. Hello everybody, this is Rashi Bari from Columbia University, your host for Daily Physics episode 9. Today our topic is a very exciting topic, wave equation for light. We're going to try to understand how it happens from Maxwell to Einstein. Yesterday we talked about, of course, a big part of special relativity, and that was time dilation. And the day before yesterday we talked about the principle of relativity. Of course, before that we gave you some background, the inertial reference frame and non-inertial reference frame. First student, we're going to invite Ivy League student from Brown University. Welcome.
Hello, folks. This is Rav, physics grad student at Brown University.
Of course, we're going to invite another super student from NYU. Welcome, Isaac.
Hi everyone, my name is Borno Isaac Berry, regretfully the brother of the failure down there. He said he's a super student, but what he forgot to mention is that he's actually a super stupid student. You can't just lie by omission like that.
So when we talk about wave equation, so yesterday you remember that we derived the time dilation, right? Okay, using high school math like eighth grade math. But today we're going to try to understand, right? One thing, why the speed of light is constant in all inertial reference frame. By the way,
First, we have to learn how to count to 4.
oh,
1,
2, 3,
3,
4.
Oh, 6.
But why we have to count 4, by the way?
I think it's something called like the Maxwell equations.
Oh, Maxwell equation. Oh, I see. So there are 4 Maxwell equation, and we have to make sure that we understand how to count 4 because there are 4 of them.
Yes.
I thought, it's a fair assumption that we all know how to count 4. You don't.
Sure.
Okay, I'm not gonna say it.
If you don't want, don't say. Okay.
Yeah, I know you don't want to embarrass yourself by saying you don't know how to count to 4.
No, not me, you.
Someone's mad.
But I use my finger, so I never forget. 1, 2,
Wait,
3,
what?
4 is equal to 1 over square root. You have the Isaac, what is the name of this one?
Isn't that epsilon naught?
Okay, that's for sure. Raf, what is that?
Okay, permittivity of free space.
Raf, what is the name of this one?
Permittivity of free space. The permittivity of free space?
Permeability of free space.
Bogus.
All right. Okay, great. Of course, we're going to try to derive it fast by using 8th grade level math and then, of course, using Maxwell equation. But first, let's do with 8th grade level math. Okay. So
what's in 8th grade?
Yeah, 8th grade. Okay. So now I'm going to give you Isaac, you're going to use Coulomb's law, right? To prove to get to this one. I'm going to give you 2 charges, and from 2 charges you're going to give me that equation using Coulomb's law. And Raf, I'm going to give you 2 wire that carries the current from south to north, right? And there is a magnetic field, and because there is a magnetic field, there is a magnetic force. Using that magnetic force, you're going to use those understanding to get the force equation, and that's going to give you the permeability. So which one do you want to take, Raf? You want to take the mu or you want to take the epsilon?
I can do whichever one makes it easy
Isaac,
for
which one you want to take?
Hey, do you think I'm a coward? Do you think I'm a loser? No,
Yeah.
those are precisely. Oh my God, bro, just nodded. I shouldn't have said that.
I mean, you just walked into that.
Shut up.
Thanks for setting
Shut
it
up.
up.
All right, baby Isaac. Which one do you want to take, baby Isaac?
Why don't I let Ref choose so he can not embarrass himself in front of all these audiences?
All right, Rav,
Okay. I'll take let me take the magnetic field one because I don't think Shubha knows about magnetic fields.
All right.
Actually,
Okay.
maybe he doesn't know about magnets, period.
All right. So let me kick
I'm
myself.
going to kill you.
So let me kick myself out. Isaac, you're gonna put two charts, and from two charts, you're gonna write the Coulomb's law, and you're gonna show me the permittivity. Hold on. Let me pin yourself. Let me kick myself out. Is that
Shubha,
good?
are you using excuses because you forgot Coulomb's law?
Shut up!
Oh,
God damn it!
okay. Just making
First,
sure.
let's derive Coulomb's law. So, I'm going to take these two right here, Q1, Q2. Now, I could derive Coulomb's law, but I don't feel like it. So, we start by saying that the potential, according to Coulomb's law,
Oh
is
no,
equal
force. I want to
okay,
see
the
the force.
force is just minus du dr, which in this case gives it Q1, Q2 over 4 pi epsilon naught, which is the same epsilon naught that's on the board on the host screen, r squared, where r is the distance between the two.
All right, very good. Go to now chalkboard and write the epsilon.
Do you want me to write epsilon naught in terms of force?
You know, just value of epsilon. Just value of epsilon.
I don't know. I don't memorize that.
Oh, okay. So I'll tell you,
Oh.
and you're gonna write it. Epsilon is 8.8.
Memorization is a crime. They should lock him up.
No, write it down. Epsilon naught is 8.85 on the chalkboard.
Epsilon naught is
No, give yourself more room. Give yourself more room all the way over there because it's a freaking long number. 8.85 times 10 raised to negative 12. 1 over cubic meter. 1 over kilogram. Second to the 4. And a to the second.
Ampere.
Ampere current.
okay.
Oh, ampere.
Amps.
Amps. Okay, great. All right, Ref.
Okay.
Do
The failure gets to try.
Okay.
Does he know what a magnetic field is? Does he know it can be generated by a current carrying wire? Let's find out. All right, buddy. Do you know how to use the right hand rule?
Fast write
First, you stick one
Isaac,
finger
Ref,
up this way. Oh,
Ref,
wrong
Yeah.
finger.
Can you fast write the magnetic field equation?
Yeah. I don't know if I remember. Just kidding. Just kidding.
And can you write the force equation?
Let's see
Right.
if you still remember Coulomb's law.
Can you write the force
5 seconds
equation?
later.
Yeah.
I don't remember.
Can you write the force equation?
Yeah.
Hey, how do you know it's phi hat? That depends on which direction the
All
wire
right,
is
now
pointing.
can you replace B? F,
Yeah.
F is equal to?
Let me say I1.
I the same. I1 is equal to I2.
Okay. Then I can.
Genius, you wrote that yourself.
No.
Did you not write I and I instead of I1 and I2?
It's
You
not
knew they
about.
were the same.
It's not about what I write. It's about what I don't write.
You want me to like read between the lines, look for negative space? Yeah, it's
Dad,
about
can you
what.
see this, or is it too low in the
No.
screen?
I do
No,
see
I
it.
can see
Okay.
it.
So F
Okay.
Yeah,
over
you see,
L.
he's correct. It's all about what he doesn't
F
write.
over
Because
L.
anything he writes is instantly wrong.
Hold on. Isaac, pay attention now. F over L is equal to what?
Mu naught I square.
All right, now write the value of mu naught.
Okay.
You remember? No, not 6.67 is the G, big G.
Oh.
6.67 times 10 raised to negative 11. That's the Newton constant. I think Newton is not happy in the graveyard.
Wait. Is it
Newton's not just not happy. He's rolling like a wheel in there.
There's the mass of the earth.
Oh, Jesus. Okay. Wait. Then
I'm gonna cry.
Oh, I got it.
How can it be mass of
Next,
time?
he's gonna write 9.81.
Oh, he's cheating. He is cheating. He is cheating. Okay, no,
Wait.
that's not allowed. Okay.
No, you can't just
Okay.
do that.
Okay, write it down.
No,
1.2566
Okay.
you sadden me,
times 10
Brett.
raised to negative 6. Now, can you write the SI unit using Isaac as a cheat?
Yeah. Okay. Let me see what Shibo can I see
If
your.
if you are really pay
Oh,
attention.
I can be smarter than Isaac because
No, you can't.
the magnetic field is in Tesla.
No. Look at Isaac one.
Oh,
Isaac as a unit.
okay.
Learn
Because
from
at
me,
the
peasants.
end of the day, you have to have meter over second.
Okay, Shibo, can you show your well, for some reason
Can you
I see
not read?
dad. No, I see dad's wait 1 second. I think the phone has to. Okay.
He wrote.
Shibo, can you pin dad? Can Shibo pin himself?
I'll pin him. Okay, I pinned. Oh no.
Pin only works for
Oh,
one
okay.
person.
Now I can see him. Okay, Shibo. So what is it?
Okay,
Second.
failure.
Okay, so epsilon naught is second to the fourth over cubic meter kilograms and ampere squared.
Why do you pronounce it like ampere?
Isaac,
Ampere is rolling in his grave right now.
Isaac, can you put the camera nicely, baby?
Okay.
Baby Isaac. Okay.
Is ampere SI units? No.
Yes. How
Yeah.
do you not know what the SI units are?
Okay, good.
I'm gonna cry, bro.
Okay, so okay, we have to get meters per second. So C is 1 over.
Oh, genius. We got a genius right here.
Okay, so that means C squared is 1
Okay,
over
genius. You do realize this means mu naught epsilon naught has to be second squared over meter squared, right?
That's right.
Or are my words not getting over through the camera?
Oh, wait, second squared over meter squared.
Yeah, that has to be their product, mu naught
Yeah.
epsilon naught.
Yeah, everything has to be canceled out.
Oh, okay, wait. Oh, let me think about it.
You're a stupid one, man.
So, okay, I have to. Oh, okay, then. Okay, amperes has to cancel out, so let's put it on the bottom. Kilograms
Can
has
you
to go
tilt
on
your
the top.
screen more to the right?
Oh, yeah. Okay, so ampere has to cancel out, so I put it on the bottom. Kilogram has to cancel out, I put it on the top. So this will give me
You
I
still
need-
have second to the fourth over meter cubed. Some
so
of
I
them
to
have
put
to cancel
second
out as
squared
well.
here, and I have to put a meter here.
Yes! Hooray!
Okay.
Hooray! You got it.
All right.
Good job.
Isaac gonna now do the math. He gonna show that this is actually speed of light. Go ahead, Isaac.
Okay. I mean, it doesn't take much effort to just plug two numbers into a calculator. Oh wait, I don't have a calculator.
No,
Okay,
not
never
calculator.
mind.
You're gonna do it by this.
Okay, then we can estimate 1 over the square root of 8.85 times 10 to the minus 12 times 1.25 times 10 to the minus 6.
Mm-hmm.
Immediately, you can rewrite this as 8.85 times 1.25. Huh?
Baby, don't estimate. Here is the calculator.
It doesn't matter, I can estimate it.
I bought the calculator for you.
Times 10 to the 9. Now,
Wait, I got it faster than you.
bro, I don't have a calculator. How is that fair?
It's just 3 times 10 to the 8. Skill issue.
No. Let's go.
I am really restraining my urge to punch you in the face right now. So you get 1 over 9 times the square root of 9 times, what is this calculator, bro? 8.85 times 1.25. And this is about 0.3. Okay. So look, this is the better estimation, right? So if you really think hard about it, 8.85 times 1.25 is just 8.85 plus 1/4 of it, which is basically 2.2. And what happens when you add these two together? Well, you get 6 here and you get 10 here. So you're essentially taking the square root of 10. And the square root, 1 over the square root of 10 is basically 0.3. And so 0.3 times 10 to the times 10 to the 9 is just 3 times 10 to the 8.
Wait, you wrote -9 before.
No, I didn't, dumb.
Oh, okay.
Okay, excellent. Excellent. Okay, great. So now, okay, now please explain how Maxwell himself discovered that speed of light is constant in all inertial reference frame using the
What?
eighth grade math you just did.
You want me to use 8th grade math to
No, you
explain
just did eighth grade math. You use, two charges and he used two wire that carries the current. And 1860, how Maxwell used this one, this is wave equation, how Maxwell used this one to measure the speed of light, and how this gave him understanding that it never changes, it's constant.
Well, I actually don't know how he got the understanding that it's constant in every reference frame.
Well, that is the Michael. Okay, but Michelson-Morley experiment
So,
established the
okay,
speed of
then
light.
tell me, then I'm gonna ask you then different question. What went wrong with Maxwell?
Huh?
Okay,
What
so
what misconception he used? We are 1860. We are
the
not.
ether,
We are.
the ether,
Oh, there you go. There you go. Right.
the ether.
So
Yeah.
he used ether. He thought 3 times 10 raised to 8, right? Is
Mhm.
with respect to ether.
Yeah, the golden rule is that every wave needs a medium, but light somehow doesn't satisfy that.
For example, this is a car, right?
Mm-hmm.
And this is Isaac. You see me? Oh, all right. Let me put myself back. Okay.
Yeah, I see you
My,
there.
do you see my car?
Yeah.
So this is baby Isaac. The car move at 340 meter per second.
Wow.
And baby Isaac, can you say something loud?
Is that car moving at the speed of sound?
That's the intention. So 340 meter per second. Now what happened?
I'm pretty sure that's very unsafe and
No,
will
no, no.
get everybody killed.
It's like imaginary car.
I don't think there's a car that's built for 340 meters per second.
Put that aside. Put that aside. Forget about car. Let's say plane. Plane always move with that much. Okay.
Yeah, anyway, any sound wave that I make inside it is still gonna escape the car. It's only if someone outside the car at
Now,
rest.
now this is RAF. Who is moving? Is the car moving, rap moving, or sound moving? Oh, forget about it. Is the sound moving or rap moving?
There's no answer to that unless you pick a reference frame.
Very good. Now, there is a temptation to say sound is moving. Of course, if the sound doesn't move, then who is holding the sound back? We can say that the Einstein made that argument that this is air holding it back, right?
Mm-hmm.
What does the air doing?
Well, sound is basically just oscillations of particles in the air. And those oscillations can only be transmitted so fast before they start to break down. Air is one of those materials where the oscillation of particles breaks down especially fast compared to, let's say, water, which is why sound waves travel much slower.
But is the air going at the direction of the sound or opposite to the direction of the sound?
Is the air going to the direction of the, well, what reference frame are we in?
We are reference frame.
Well, air is.
Talk about the car. Is the car at the direction of the car? Velocity of the car, the air velocity at the direction of the velocity of the car, or opposite?
Well, from Isaac's reference frame, he's going to see it as opposite, obviously, unless there's like a hurricane going on. But
Isaac is here, right?
yes,
Okay. So now, how can you use this one to make an argument that it is almost impossible, or it is impossible to figure out who is moving?
well, it doesn't, you don't need any example for this. All you need to know is that the answer to who's moving depends on what reference frame you pick. Because in one person's reference frame, their velocity is 0 and the other object's velocity is non-zero, while in another person's reference frame, their velocity is 0 and another object's velocity is
If it
non-zero.
was so
None of the
easy,
specifics like this matter.
if it
And we
was so
already went over this 3 videos ago.
if it was so easy, then as smart as Maxwell, why he failed to imagine
Because he
and
failed.
still use the ether?
He didn't fail for that. He failed over something completely different. He failed over the misconception that because 99.9% of waves require a medium, 100% of them. Because the 99.9% rule doesn't always work. And
Wait, that doesn't make
electromagnetic
sense,
waves.
bro. What? Wait.
I
Let me
don't know
jump in
what
here.
I don't know
So,
what he's talking about.
okay.
The EM waves are like, I don't know what percent of the waves.
No, that's not what I mean. I'm saying that most known waves by then, or most known types of waves, needed a medium to travel.
Gravitational
Sound
wave,
waves, mechanical waves, anything.
gravitational wave don't need medium.
Did
Wait,
they know
gravitational
about those
waves
in
were.
1860?
Wait. Okay, wait. Let me.
Did they know about gravitational waves in 1860?
That's true. That's true. Yeah.
Yeah, every single documented type of wave up to that point needed a medium to travel.
That's
And
true.
so, naturally, when they saw light, they thought, well, it needs a medium to travel too, just like everything else. But unfortunately, just because it applies to 999 cases doesn't mean it applies to the 1000.
That's the shortcoming of Maxwell.
Yes.
No. Okay. Wait. Um.
What's wrong?
So, okay. First of all, yeah. So the idea of the ether was prevalent in
No,
the 1860s.
it was invented by Sir Isaac Newton to serve his purpose, and it did serve purpose. And as Isaac, it did serve purpose. All the waves is the medium. All the wave is medium except EM waves. Yeah, absolutely.
Yeah, I mean, there is no way to know that it doesn't need a medium until you do the experiment.
Uh,
There is no theoretical way you can say light
And
needs a
yeah,
medium
doing
or
the
light doesn't
experiment
need
is
a medium.
expensive and difficult,
why you need
especially with something
why you
as
need
hard to
experiment?
work with as light.
I think Lorentz transformation, which we'll do tomorrow. I think Lorentz transformation make it obvious that the speed of light is constant in all inertial reference frame. Isn't it true?
But did they know the Lorentz transformation in 1860?
Well,
Lorentz was like a toddler.
No.
also you need to experimentally prove the
Oh, that
transformations
Exactly.
are real.
Light is hard to work with for people in 1860.
Because there was also the Galilean transformation.
yeah,
But
Galilean transformation tells us that the speed is relative.
yeah.
Yeah,
So
light
you
is hard
can't
to work
you
with,
don't know which
experiments
one
are
is correct.
expensive, and there are so many chances for things to go wrong. So why not just assume light is like every other wave
Yeah, so
until
you don't know which transfer because you can use Galilean transformation, Lorentz transformation, or there were actually a few other ones that are not
I
famous,
think that
but you don't know.
I think Lorentz transformation is
Yeah.
an extension of Galilean transformation.
well, it's a change. It sort of approximates the Galilean transformation when you zoom in a lot.
No. The Lorentz transformation actually reduces to the Galilean transformation when the velocity is much smaller than c.
That's what I said, dumb.
Nope, that's not what you said.
Yeah, I said that when you make the velocity small, the Lorentz transformation approximates the Galilean transformation.
Now you're copying me post-mortem.
The people can adjust because people has
Dad, can we like not talk to him ever again? Just like leave him deserted?
Hey, I'm the physics expert here.
Can we cut him out of the family?
I don't know who gonna win the Nobel Prize first. Whoever win the Nobel Prize first, I'll shut the other one.
No mercy. Well, I better get to my research then.
Wait, Shiva, but if you're going into math, that means you're automatically like disqualified. What a loser.
Listen, the first thing I have to do is bribe the Nobel Prize Committee to start a Nobel Prize in math. Or does the Abel Prize count? Fields Medal?
They count.
Those are what? Fields what? What did you say, Fields?
What did you say, bogus boy?
I said I published 2 more papers than you.
Stephen Hawking medal? What? Huh? Me?
Oh,
What?
what?
All right. So to do the Lorentz transformation, do our audience who are eighth grader, including people who born today,
Stephen Hawking? I don't see him in the list of
do we
Nobel
have to give
laureates.
them? Do we have to give them understanding of space-time diagram before we do the Lorentz transformation?
Yeah,
Yes.
that would be
Is that
very.
background necessary?
Yeah,
Nope.
absolutely.
Nope.
Yeah.
We just take them right out of fifth
Yeah.
grade and shove them into differential
Because the
geometry.
space-time diagram is a very nice geometric way to understand the Lorentz transformation.
Okay. So
Well, yeah,
tomorrow,
especially when you're dealing with 1D space. So you can draw everything that happens in a world.
baby Isaac, then can you agree with your big brother, the Ivy League brother, that tomorrow you're going to do the Lorentz space-time diagram?
Fine. I agree. We'll do the space-time diagram.
Good. I'm glad you finally came to your senses.
All
I'm
right.
glad you finally stopped being a bogus boy and started saying things agreeable.
All right. Can you give the audience, you are in front of entire nation. My fellow American, that's how you're going to start. My fellow citizen of physics. No, I'm so sorry. My fellow citizen of physics. And here is my 50-second summary. And go ahead. Who wants to go first?
Me.
Okay.
Okay, so my
Okay, let's hear the
fellow
mistake.
citizens of physics, I hereby declare that Ref is a bogus boy, and also we just derived both the free permittivity and the free permeability of space today. And we also showed that C happens to be equal to 1 over the square root of their product. Then we briefly discussed in conceptual form, without getting into the mathematics, how the Maxwell equations lead to the conclusion that C is both constant in every reference frame and C has some fixed value. So yeah, that's about it. Don't listen to the bogus boy who's about to give a summary. Thanks everyone for watching.
Okay, my turn.
Ref, yes.
Okay, so my fellow Americans, today we looked at 2 electric charges and we saw that their force was proportional to the electric permittivity epsilon naught. And we looked at 2 wires and we saw that their force was proportional to mu naught. And then we saw that the speed of light is 1 over the square root of mu naught times epsilon naught. And the speed of light is constant in all reference frames. So,
Bogus alert! Everything he just said is bogus. Don't listen.
okay, conspiracy theorist.
All right, everybody. With that saying, this is your. Let me pin myself only. Okay, remove. Okay, and remove. All right. Thank you, Raf, and thank you, Isaac. Join us tomorrow for a space-time diagram, and we're gonna make it as fun as possible. See you tomorrow.
Okay. Bye, bogus boy!
Bye, incompetence.
All right, bye,
Hey, at
baby.
least maybe